Hi. In this example, we are going to make a timing analysis of a circuit under some input signals. The timing analysis is good to know how the circuit evolves in time and to have a more detailed picture on how the output will behave. Timing analysis is interesting to when we consider the delay in the gates, the time that the gates spend in calculating and generating the new output value. So we will use delay, but we will use a simple model in which all gates have the same delay that we will call delta. Even this simple model is enough to have a more clear idea on what happens with a circuit when it's actually working. So the conditions are that we know the circuit is subject to these inputs. Y is always set to 1, and X and Z vary with time as in this chronogram here. Okay, X starts being 0, then is 1 sometime, then 0 again, and the same thing for Z. Okay, so given the circuit, we may do a functional analysis. We could calculate the expressions at the nodes going from the input to the output and obtain an expression for F as a function of the inputs. But this is not interesting in a timing analysis because we to see how it evolves in time, we need to know the changes at all the internal nodes of the circuit. That's why I have named the internal nodes. This will be I1, I2, A1 and A2, and we will calculate the signals at each node. So the main idea here is that to do our analysis, we always calculate the signal generated by a gate as a function or depending on the exact input it receives. Here the same. Once I know I1 and I2, I will be able to calculate and to plot what I will have in A1 considering the time. Okay. So in the first step, I want to know the expressions of every node as a function of the inputs. I know that I1 is X complemented. Okay, so I do the analysis, but only gate by gate. I2 is Z complemented. A1 will be I1 and I2. Okay, and it's important not to make any substitution here. So I know that A1 depends directly on I1, I2. So I put the expressions, but never substitute the values, not to miss the information on what nodes this signal depends on. And now A2 is equal to X, Z, and Y. Okay. And finally, I know that F will be equal to A1 or A2. Okay. This comes from my analysis of every node, considering the operation of all the gates, A to X, Z, and Y. But now I have some particular conditions. In this case, I know that Y is equal to 1, so I can simplify these expressions a little bit. In fact, the only one that I can actually simplify is this one, okay? Because A is constant and is equal to 1, A2 is equal to X, Z only, okay? Now, I can start plotting all the signals going from the input to the output. I cannot plot A1 yet because it depends on I1 and I2, and I don't really know what I1 and I2 are. So I start at the main inputs and we'll plot first I1 I know that this is x complemented. So basically a1 will be the opposite value to x, but the point is that the value will be reached sometime after x changes, which is the delay. That's why we have the delay. I'll take the delay as one of the small squares in my paper. So if x starts being 0, a1 will start being 1, and it will be 1 up to this point. At this point, x changes the value to 1, so I1 will change to 0, but will not do it immediately. It will take one delay to change. So the change will take place at this point, okay? The time spent from here to here, I'll see if I can, the time spent this transition causes this transition, okay? And the time spent from here to here is one delay, one delta. I will not write it here, just not to make it a bit messy, but it's something like that. I will use some different softer color here, so this transition will cause this transition here. Again, that's it, okay? Now, I1 will be 0 now and up to the time when x changes the value again. Actually, I can mark the interesting points, okay? At this time, when x changes, okay, this is the time I may consider to evaluate a1 again. So up to this point, it will be 0, then it will change to 1, but not immediately, but after a small delay here. And from here, it will be 1 now all the time long, okay? There's an interesting thing, which is what happened at the beginning. What's the correct way to express it in my chronogram? You know, because my chronogram starts here, at this point, it will be time equal to 0. I know that x here is 0, but I don't really know what's the initial value of I1, okay? This initial value of 1 suppose that x has been 0 for some time before, what I have plotted here. But if we don't really know what happened before this time, then I cannot know what happened with I1 up to a delta time after the initial value of x. Sometimes it can be expressed as an unknown area, so we may indicate it like this. I will indicate it like something like this, okay? An area here where I don't really know what's the value of x. It is unknown for me. I know this is 1 because I know delta before it was 0, but I don't really know what's here. It depends on the problem. Actually, this is more correct with the information the program gives, but we can also suppose that the signals that have been plotted here has been stable for some time, so I can start with some other initial value. It will be the more correct solution given the information I have in the diagram. So next I can now plot the I2 as well. I2 will be here. And we know I2 is Z complemented, so it's exactly the same. It will be the complement of Z, so it will start being 1 or unknown at the beginning and will start being 1 from here on, okay? And anytime Z changes, it will also change, but delta interval afterwards. So it changes again here, so it will change, but the delta interval afterwards. So this way I can just draw the signal, okay? Making all the changes in Z, but waiting for delta after that change. Okay, so this time here, you say a delta after, here it's happening a delta after, here the change happens a delta after the change in Z, and the same happen here. And at the beginning of my transitions here, I have an area where I don't really know what's the value here, okay? Now, once I know A1 and A2, I can now calculate I1 and I2, sorry, I can now calculate A1, because A1 is the AND operation of I1 and I2. Okay, so I have to make the AND operation of these two signals. So we start by noting that these two are 1. From here, at this point, let's mark that time. At this point, we know these two signals are 1. Okay, so 1, 1, 1, and 1 will give a 1. So I know A2 will be 1. Okay, I don't know what's the value up to here. I know it will be 1 starting at this point. Okay, a delta after I know the values of A1 and A2. And I will start drawing the signal every time A1 or A2 changes. I will have to reevaluate the value of A1. I will mark these times here in the chronogram. So at this point, anytime the inputs of that gate change, I will need to reevaluate the output. So these are all my interesting points here. Okay. Changes A2, A1, 2, A1, all those points here. So here, for example, I see that I have a change from 1, 1 to 1, 0. 1, 0 will, the AND operation will make a 0. So the next value will be a 0, but it will not happen immediately, but the delta after. So I wait the delta, and the change is a delta after. Okay. Now we move here, it's 0. Now the next value is 1, 1. So the AND will be a 1, but it will not change immediately, but a delta after that. Okay. It will continue to be 1 up to this point. Now the new value is 0, 1. 0, 1 will make a 0 that will be reached with a delta delay. And anything I draw up to the next position. Now it changes to from 0, 1 to 0, 0. It also makes a 0, so it will continue to be 0. Here I have 1, 0. It also makes a 0, so it will continue to be 0. Here I have a 1, 1 that will make a 1 that will be applied with the delay of delta. Okay. Okay, and what happened during this time? During this time, I don't really know what's the value of I1 and I2 are. So I don't know the value of A2 either up to this point. So we will also mark all this area as unknown. Okay, we grayed out or whatever. Okay, now I know this is actually this is I1, what I have been calculating. Now I can calculate A2. A2 will be here. A2, once considered the y value is xz. Okay. Now we'll mark the interesting points. Anytime X or Z changes, X or Z changes, it's interesting to me because that signal may also change. So we will signal here, we will mark the times at which those variables change. Okay, so I will put the lines here. These are all the times I need to evaluate the value of A2, and a possible change may happen. Okay, so for the start, this is 0, 0. This is the end operation. It will make a 0. So I start at 0. Later on, I will see if there's an unknown area here. Now I have a change here. It changes from 0, 0 to 0, 1. 0, 1 will make a 0, so it will be 0 still. Now I have a new change. Now I have a 0, 0, so it will be 0. Now I have 1, 0, it still will be 0. Now I have a 1, 1. 1, 1 will make a change to 1. Okay, 1 and 1 will make a change to 1. Okay, there's be a change, but with a delay of delta. And it will be 1 up to here. I re-evaluate 0, 1 will make a 0. At this point I have a 0, 0, so it will remain being 0. Now I finally can calculate the value of the output, F. Now F, we know, is A1 plus A2, the OR operation of this. But first we have to see what happened at the beginning. So it's the same, it depends on X and Z. I don't know what's the value of X and Z before the initial time. So up to a delta, after the initial value I know, I don't really know what's the value of A2. Okay, so I will mark this one as unknown. And now for F, yes, I add these two. Okay, it's a bit tricky because we'll start with the unknown. I don't know what A1 and A2 are, so I don't really know what F is during all this time. Now at this point, I know that A2 is 0, but I don't know what A1 is. So if it's a 0 and this is unknown, I don't really know the value of F. Okay, 0 or 1 will be 1 and 0 or 0 will be 0, so I don't know yet. During all this time, I don't really know yet what's the value of F. At this point, I have some known value, 1, 0. 1, 0 will make a 1, okay? But this 1 will appear with a delay, so this 1 will start being known at this point. So up to this point, okay, we don't really know, during all this time, we don't really know what the value of F is. So I mark it somehow. And now, as we have done before, anytime that A1 or A2 changes, A1 changes here, I may have a change in the output. So I will signal, I will put help lines to know where I must evaluate the changes, the possible changes in F. Okay, this is not actually completely necessary, but it's very, very good way to not make mistakes. So up to here, this will be 1 or 1. Now I have 0, 0. 0 or 0 is a 0, so it will change to 0, but not immediately, with a delay. And will continue to be 0 up to the next checkpoint, okay, where I have to check if it changes or not. So at this point I have a 1 0. 1 0 will make a 1, but with some delay, and will be 1. Now I have a 0 0, so it will make a change to 0 again, but with some delay, and it will be 0 for some time, and then it's a 0 1, so it will change to 1, but with some delay here. You see that always we have some delay in all these changes. Okay, I'll try if the arrow is good enough, but all these changes happen here with some delay here and here and here with a delay of delta. Okay, so now at this point we have 0 0 again, next value is 0, so it will change to 0 after a time of delta. And here I have a 1 0 again, so it will change to 1 after a delay of delta. Okay, so this is basically the solution to my waveform. If x and z are behave like this will be the different values that f will take. Okay, so now this is solved, okay, for that circuit. Now the exercise is finished, but it is nice to know what happened if we analyze what's the expected result in f if we do not consider the delays. Okay, if we do not consider the delay, we could use the expression for f, okay, from the functional analysis. We'll try to do it. Let me reduce the zoom a little bit. Okay, so the expression for f, let's make some room here. Okay, so the expression for f if we do the regular analysis could be something like this. F is equal to a1. So to make the functional analysis, we just make the substitutions. It means a1 is x complemented, this is z complemented, so a1 will be x complemented and z complemented, a2 will be x and z as before, because y is equal to 1. I'll do the complete analysis, okay, without assuming any value. And then f will simply be the OR of these, so will be x complemented, z, z complemented, or x, y, and z. Okay. So this is the function, the complete function. In our case, because y is equal to 1, this will become simply, or better express, f when y is equal to 1 will be x complemented, z complemented, plus x, z. Okay. So we see that f is equal to 1 whenever x and z are both 1, or when they are both 0. Okay, actually this is, you may remember, this is the XNOR operation. Okay, this is x x nor z, right? Which is equal to the exclusive or complemented, okay? So from here, we could put in the diagram the value of f, but with no delay. Okay, this could be with no delay. This is x, z. And with no delay, it's more easy to do when now we have to consider whenever z changes, whenever z changes, or here or here, or whenever x changes. These are my help lines here. Z changes here, x changes here, and z changes here again. And that's all, I think. Okay, now I do not consider delays, so it's much easier. If they are the same, f is 1. If they are different, f is 0. So here they are different. Okay. No, here they are the same, sorry. So it's a 1. Here they are different, so here is changes to 0. They are the same again, so it changes to 1. Here they are different, so it changes to 0. This interval, they are the same, so it changes to 1. And in this interval, they are different, changes to 0. And the rest of it, they are the same, so it changes to 1 again, and being here, okay? So it happens when we do not consider the delay. So we may think now, from now on, okay, these are the same, okay? So you see here in this interval, f is 1, 0, it's 1 here, 0 here, it's 1 here, 0 here, it's 1 here. And this is the more realistic solution. When we consider the delays, we will delete this one to have it more clear. Okay, the more realistic solution. So we may say that this is different or not. Actually, our delay, our signals change very quickly. But what we see is that this 0, this 1 here, okay, is the initial value that we also have here. This one is this one here. Then it changes to 0, but in the real circuit there's some delay, because you see it changes to 0 because z changes to 1. The real circuit will take 1, 2, 3 delta to change to 0 here. It takes 3 delta because in my circuit the signal z to affect the output have to go through 1, 2, 3 gates. So it's expected that it takes up to 3 delta. This is the whole delay from z to the output, okay? So this 0, this will have value here, okay? This 0 here in the real circuit happened, but with a delay. The same happened. It then next changes to 1. It also changes to 1 in the real circuit, then to 0, changes to 0, then it changes to 1 again, okay? This changes to 0, changes to 0, and finally the final value is 1, like in the more realistic circuit, okay? So we can see that more realistic analysis give the same result, but it takes account of that the result is achieved with some delay. Sometimes the delay can be as long as 3 delta here, okay? And sometimes the delay is a bit smaller here, like here. From here to here, the delay is only 2 delta because some changes in the input affect through 3 gates, while other changes affect the output through only 1-2 gates. Okay, we may expect different delays, but the result is correct, only that it's delayed with respect to the ideal result. Okay, so to do this kind of analysis, this is also timing analysis with no delays, but it's very little interesting. And to do this kind of analysis, we don't need to obtain the values for the intermediate signals. We can just go to the final expression, okay? But doing a timing analysis without considering the delay is not very useful indeed, okay? Because we don't get information about how long it will take. In a real circuit, sometimes we need to know how long the output will wait before taking its final result, because sometimes these delays are simply too much. We want our circuit to operate faster, or we need to know that data to expect how fast my circuit will operate. Okay, that's it. Thank you.